welcome. Here are a few slides about something I learned about a bit this summer. It's an exciting topic in differential geometry. There's an amazingly sparse list of even-dimensional positive curvature manifolds. So there are the God-given examples like the spheres or projective spaces over the division algebras. And then there are only 4 more. So there's the flag manifolds W6, there's W12, W24, and then there's the Eschenburg manifold E6. So this is the complete list. This is the full list, and there's a nice survey article of Wolfgang Ziller here, which lists this. And then also the symmetries. All these known manifolds have relatively large symmetry, surprisingly large symmetry groups. Here's a list given by Shankar, a student of Grove, and so in general, one knows they have to be compact Lie groups. And so some of them are large, like this F4, which is a very large exceptional Lie group, which is the symmetry of the Moufang-Cayley plane, or the W24. Then we're going to look at the circular symmetry, which is the smallest possible kind of continuous symmetry. And one knows the Hopf conjectures, they're just in dimension less or equal to 4 without any symmetry. With the circular symmetry, one knows it until dimension 10, which is quite an amazing thing. And that's what I learned about this summer. And actually, there's a very nice proof until dimension 8, which I can essentially give you the full proof today in this video. The dimension 10 case is a little bit more involved, needs some homology results of Wilking, and so it's more subtle. And then, but from dimension 12 on, one doesn't know. Similarly, without the symmetry, dimension 6 on, one doesn't know the Hopf conjectures. So here is the result until the whole proof until dimension 8. So there is a kind of a nice picture, is that if you have a symmetry, then there is a fixed point set, this fixed point manifold. They are known to be manifolds. They are totally geodesic invariant manifolds, which have a codimension 2 or less. So always even codimension. Each component has even codimension. There can be also points. But the sum of the Euler characteristic is the Euler characteristic of M. So this is a very nice way to compute the Euler characteristic. You just actually compute the fixed point sets for some circle action, then add up the Euler characteristic. But then if you look at this, the 8-dimensional case, so there's the possibility that there's one 6-dimensional component. This has been then covered by a theorem of Grove-Searle, which we are going to look at quickly, which is very nice. And then, because then the manifold has to be a space form or a complex projective space. And then there's other possibilities if you have no component 6. There cannot be 2 component 6 by a theorem of Franco. But if there are 2, if they are less the dimension, then they have by Gauss-Bonnet-Chain, they have already positive Euler characteristics, so they add up to something with positive Euler characteristics. So it's a very beautiful proof. You have almost nothing to do, which is just once you know the theory. So here are some faces who have worked on this. This is Grove and Searle and Wilking and Wrong. So they have the records. And then one has more work with high rank symmetries, which are still a lot of things are. It's a very active area. Seems to be a very nice area of research. But it's all kind of started with Connor Kobayashi, who have in the 50s worked independently on this, and they have just kind of seen if you have a fixed point set, these are manifolds. This is kind of easy to see because they have to be totally geodesic. If you have a geodesic inside N, it cannot leave N, because otherwise it would twirl around, right? Because you have a circle action outside of N, so it has to stay inside N. And then because it's invariant under the exponential map of the thing, so you have a manifold structure. It's quite a nice thing. And then it has to be, for general principles, the symmetry has to be a Lie group. And so this is Connor and Kobayashi. Kobayashi has a nice book from the 70s, which essentially covers all this. And then the Euler characteristic has to be the same by Lefschetz's fixed point theorem principle. So the fixed point manifold. So all these points is kind of, they add up to the Euler characteristic of the fixed point set. It's a nice theory. And there are a nice application. I mentioned this already. You can compute the Euler characteristic of smaller of spaces like the projective spaces. A cool way to compute the Euler characteristic without a lot of work. And you can do that for other manifolds. For the sphere, of course, you just rotate, and then if you have an even dimension, you have two fixed points. In odd dimensions, you have no fixed points, so your Euler characteristic is 0. You can compute, use it for the octonionic projective plane, which is a very nice beast of a manifold, which Ruth Moufang was also. Cayley has done the octonions with the Ruth Moufang. It's also the Moufang plane called. It's the last of it. There is no higher projective octonionic space, so that's kind of related to the fact that we have no more positive curvature manifolds. And then there is this Franco idea, which is also very beautiful, which is also used in Singh's theorem. It's a variational principle. So if you have two fixed point sets, and you take all the geodesics going from one to the other, and so if the dimension add up to something larger, or equal to the space, it is not possible because by doing the variation here, so you can make the distance smaller. So it's kind of the same argument than in Singh, kind of a variational argument, which shows that the sum of the dimensions of the largest component, fixed point components, have to be smaller than the dimension of the space. This produces amazing restrictions to what the fixed point set can look like. And then there's this amazing theorem of Grove-Searle, which from the 90s, which says that if the codimension is 2, if you have a codimension 2 component, then it has to be a space form or complex projective space, which is very rigid. It's a rigidity theorem which kind of restricts the possibilities. And the geometric view is actually even nicer then, because you can see geometrically, if you have this fixed point set and then you have codimension 2, you can look at the geodesics starting from n, leaving n and coming back. And then it has to twirl around, but it has to come back because that's in positive curvature if things have to close up again. And so then in this case, but you have to come back when it closes up, you have to come back to n. And so you have a return map, which is which is not distance preserving. And if it's distance preserving, so it has to, and it's also an involution, so it has very, very little possibilities to do that. And this leads then to also organization of relatively large class of positive curvature manifolds, even dimension of positive curvature manifolds. There are spheres, that are real projective spaces, that are complex projective spaces, and it's all organized according to dimension and Euler characteristic. So this is kind of the periodic system of elements for positive curvature manifolds with kind of this kind of a Grove-Searle symmetry. And I tried to push that a little bit more, this idea, or someone made a little bit fool of myself. But this picture is kind of that's the picture. Once you have codimension 2, you start a geodesic and you come back. You twirl around, you come back. And what happens is, so you have a whole bag of, it's actually a sphere, a 2-sphere. And then you can do that in every, so all these 2 spheres foliate the rest of the thing. So you can construct the manifold M from N and the geodesics. It's kind of like a Hopf vibration idea, but it's very nice. And in the Grove-Searle case, what happens actually, you have to come back when you start at the same point. You have to come back in the same place. So the right picture here is the picture which actually happens. So you cannot have these 2 bags ending up in the different tubes ending up in different positions. And in order to prove this, you can look at the intersection number of 2 such tubes, they intersect in circles, and this number of circles is invariant. It's a rigid thing because they cannot get too close to each other. They cannot bifurcate because of the positive curvature, and there's a minimal. So if they cannot be closer than the radius of injectivity in the manifold, which is positive in a positive curvature manifold. And so this number is constant, and then you can kind of look at the thing if the 2 points get closer and closer together, and then they have to agree. So you can assume if they don't agree, and then what happens is you look at the situation when the tangent initial velocity vectors get smaller and closer together, and what happens then they have to intersect, and so you get kind of this collapse of the thing. So it's a very nice geometric argument. and kind of an understanding of this Grove-Searle theorem, and that this gives this a return map, which is then also giving you charts of a manifold. If you come back directly, then you have with two charts you can cover the whole manifold. Then it has to be a sphere. If it comes back to the same point, you can even do it with one, and in the case when you come back before to a point, then you need three charts, and they have the complex projective spaces. So now I kind of thought, oh, that's a very nice picture. You can extend this to the case when it's Codimension 2. You skip Codimension 2, and I kind of had this. This is actually kind of a known fact that you have that the normal line bundle has a complex structure, and so you can actually define a complex line bundle, and so kind of make this extension as if it would be Codimension 2. But the problem is that this construction doesn't lead to positive curvature manifolds, which that was my mistake, and so that doesn't work. So there are actually examples where this doesn't work. This codimension can be is larger than you have other examples. For example, already if you take a two-sphere and you make this construction, but then there's another two-sphere, and if these two spheres don't agree, so you get actually a different manifold, also a four manifold, but which is a two-sphere bundle over a two-sphere, which is not. So Euler characteristic 4, which is not the sphere, but has not positive curvature. So that's a little bit. But then, this idea of extension is actually very intriguing, because there are very little possibilities which you have. So you have this constraint of dimension, and you have this constraint of what kind of Lie groups you take for extension. There's only circular and SU2, and then the octonionic case. So if you look at all these possibilities and you kind of look what is actually possible, you get the periodic system of elements, which is here, and these are all the manifolds one knows, which is quite intriguing. Of course, one doesn't know. I know this is kind of just a picture, but here is another kind of this periodic system of elements. I added a little bit of physics. It's actually amazing that you can see all the fundamental bosonic forces. Bosons here realize the photons, the gluons, and then you can see the vector bosons and the Higgs and the gravitons. So you essentially kind of can make this analogy, which it's probably foolish, but here is this analogy again. So we have the CPD, the complex projective spaces. There's a lot of photons, and the Euler characteristic grows, and the number of photons grows. Also with a quaternionic case, you have the gluons, but these are SU2 extensions, so the weak force, and then you have the vector bosons W6, E6, and W12, which is the Z0. So in this case, you have an SU2 symmetry there, and then you have the OP1 and OP2. These are the only octonionic projective spaces, and so these are the gravity thing, and then there's the W26. What else? There's only one other gauge boson. So one has to be a little bit careful here. Of course, there are lots of blunders in this respect, like Kepler, when there were 5 Platonic solids, and there were 5 planets known, so you associate the 5 Platonic solids with a thing, or when Thomson looked at the ether model with his knots. But in each case, it has kind of a motivated research. It has motivated research in Platonic solids, also in higher dimensions, and in the case of knots, it has motivated the search for a classification of knots. And also here, there is still the very open problem of classifying the positive curvature even-dimensional manifolds. Odd dimension is another story, but already the even-dimensional case is a challenge, and of course it's interesting because also of the open conjecture, Hopf conjecture. That's it.